Hello, everyone. Welcome back. Today, we're going to learn about regression. One thing I'm going to go ahead and mention that if you haven't seen my previous video on correlation, make sure you watch that first because we'll actually be using some of the concepts in that video in here. So today, we're going to understand about regression, understand the basic concepts, and how what's called a regression line, what we're often called a best fit line, is calculated. Be able to calculate a linear regression line using StatCrunch, and also learn how to do that with Excel as well. Most of it will get work on StatCrunch. And also be able to use a regression line to make predictions. That's the main value of it. Let's talk about what a regression line is, okay? So if you have a list of paired data, or some kind of data, the regression line, or best fit, or sometimes called the least squares line, is a straight line that best fits the scatter plot of the data. That's assuming the data has some kind of linear trend to begin with. The regression line equation is given by this. We're familiar with the equation for a straight line, okay? It's what's called linear expression. So X is what's called your predictor or explanatory variable or predictor variable, and Y is a response variable. And then, of course, this B1 is your slope of your line, and then B0 is the Y-intercept. Now, once again, X is the predictor variable. You're trying to use that values of X then to predict Y. Now, that doesn't necessarily mean that X causes Y, although it could, but simply trying to use the X to predict values of Y. So let's come over here to the right and kind of get an idea of what we're talking about. So let's say you have a scatter plot of some data. So you found some paired data. Of course, here's your X and here's your X-axis and Y-axis. Let's say you have some data. Let's say it looks like this. Okay, so you get the idea. Looking at it, looks like there might be some kind of, let's make a few more points here to make it a little more clear. Looks like there might be some kind of a, kind of a general, kind of a linear trend. It looks like in this case, might be kind of upward. Let's add a few more points to make it more clear. Okay, so the idea is what we're going to do is we're going to create what's called a best fit line. Now, let's say that line looks something like this. Okay, so it should be a straight line. Okay, called the best fit line or the regression line. And we'll explain in a moment why it's called the best fit line. Okay, and of course, in general, the line itself goes on in either direction forever. But that's the idea. So essentially, this is the line that kind of is the best fit for this data. And of course, once again, we're assuming the data has a linear trend. This is the best fit straight line for that. Okay. Now, let's kind of explain a few more concepts where you get the idea of why it's called a best fit line, how I actually determine whether it's a best fit line or not. So let's mention a few things. So the thing we're assuming are requirements about this, the samples of data is random sample of quantity of data that's paired. Basically, it says visual examination of the scatter plot shows the points approximate a straight line pattern. So that seems to be like a fairly, straight line pattern. Not great, not incredible, but fairly good. Okay. An outlier is kind of a strong effect on the regression equation. We'll see an example in a moment later where you do have an outlier. So removing outliers, they're known to be errors. And you consider the effect of the outliers, they're not known to be errors. So basically, if you know something is an outlier, remove it if you can, but at the same time, just be aware that outliers can have a large effect. Now, for each fixed value of X, its corresponding values of Y have a normal distribution. Then for the different fixed values of X, the distribution of the corresponding Y values all have the same standard deviation. Then for different fixed values of X, the distribution of the corresponding Y values have means that lie along the same straight line. Now, we're not really going to get into those last 3 points. Those just has more statistically to do with the test. That's kind of beyond our discussion. That just has to do with how it actually works. So what we're doing is we're actually going to show you how to calculate this regression line or best fit line. The computer is going to do that for us, but we want to make sure we can understand how to use it. So let's look at a few more definitions and we'll explain why this is called a best fit line. So first off, it says in a regression equation, the marginal change in a variable is the amount that it changes when the other variables change exactly 1 unit. Now that's kind of a lot of words. The basic comes down to what that means is the slope. Okay, the same way the slope, if you remember from algebra, is change in X or change in Y over change in X or rise over run. But basically, the slope tells you this marginal change, how much, a unit change in X affects the change in Y. Now, also an influential point is a pair of sample data that strongly affects the graph of the regression line. Such a point is often an outlier. Not necessarily an outlier, it could be a legitimate part of the data, but it's often an outlier. Now, a few more concepts, and we'll talk about how a regression line is actually created. So, something called a residual. It says for a pair of sample X and Y values, the residual is the difference between the observed sample Y value and the Y value predicted by the regression equation. Okay, so what that means is let's come over here and take a look at over our sample data. So let's draw some of the residuals here. So this, for example, if I draw a line from here, each point of my data to this best fit line, these are what are called the residuals, because in each case, what it is, for example, right here, this is some, X and Y value of the data. And this point right here on the graph then is for that same X. This is the predicted value, okay? And you'll see it's rarely is going to match up exactly, and sometimes it may not be very good, okay? So what we're doing is finding this link, the difference between the actual Y of the data and the Y that's predicted by the best fit line, okay? So what I'm drawing here, these straight lines are the residuals. The links of those residuals are important, okay? Now, something called the least squares property. This we're actually getting into how a regression line is created. A straight line that satisfies the least squares property is if the sum of the squares of the residuals is the smallest sum possible. So let's kind of, what this shows right here is if I take all these residuals, all these straight lines, the length of all these straight lines, where each straight line gives the length between the actual Y value and predicted Y values. For each one of these points, the actual Y value is actually looking at the point, and the predicted Y value for that X, same X, is on the line. What we're going to do is we're going to add up all those lines, what it's showing here. Well, first, we're going to take all those differences, all those lines, those lengths, square each one. Then we're going to add up all those squares, and that's going to give us a number. Then we want to minimize that number. And that gives us what's called the best fit line. Okay? So for each residual, remember these are all residuals here. For each residual, Y minus Y bar, and kind of similar to how I actually calculate a standard deviation, we're going to square each one. And so that's going to be Y minus Y hat. Remember, the Y hat's your predicted value. The Y, it's called a Y hat, this little rooftop on top of it is going to go a hat. Okay, the square each one, and we're going to add all those together. Okay, and then that's going to be the sum. What this means, the sum is going to be the sum of all those residuals squared, the square of all of them. Okay, let's call that a number. Let's call it A, and call it whatever we want. And so the goal is to find the line that minimizes this number. Okay, minimizes the sum of all those squares of the residuals. Okay, and then that line is this best fit line. That's the reason why it's called the best fit line. Also, the reason it's called the least squares line as well, the regression line. That's why it's called the best fit line. So imagine this. I'm not going to draw it, but let's say this is the best fit line right here, the line that best fits all the data. You can imagine any kind of line you draw through the data. You could draw a line down here. You could draw a line up here. You could draw even a line that goes down from left to right, or a much steeper line. But if you did the same thing for any one of those lines, say we make a line that was right here, okay? If you did the same thing and found all these residuals for that line, and then did the same thing, squared each residual, and then add up all those squares, that A for that line would be bigger than for the best fit line. The best fit line is a line that minimizes all this, the sum of all the squares of all these residuals is number we're calling A, and that's why it's called the best fit line. Now, one other thing you can also create, this is for linear data, for data that appears to fit on a straight line. There also can do regression lines for other types of graphs as well, but we're just focusing on linear right now. Okay, now, one thing to mention then, so that's our best fit line, and once again, that is the equation. You can write this over here. So y is equal to, make sure I go back and use the same notation they do. Y is equal to B0 plus B1 times X. Of course, X is the X value, okay? Then, of course, B1 is the slope of the line you get. And then B0 is actually your y-intercept. Now, then what the goal is then is going to be that we can actually then use this line then to predict values. So, of course, there's no point in using the line to predict the y value and x you already know if we already have that data pair. But let's say we want to predict a value that's right in here. Okay, we don't have any data. That's what it's used for. Okay. Now, before we go further, let's go ahead and mention. So we can create this best fit line, but in order to be able to use it correctly, we have to be confident that the data appears to fit on a straight line to begin with. And actually, we're going to use some of the concepts from the previous video I did on correlation to help us answer that. Let's go to Excel briefly, and also I'll show you on Excel how to also do a best fit line. Okay, so I have a few columns of data here. This first two columns of data, these are actually random numbers between 0 and 10. So what I'm going to do is to create a best fit line in Excel, and also if you look further down in the my notes, it actually explains how to do this, but we'll just show you here. So I tell you in words how to do this with Excel, and also in words how to do this on StatCrunch, which we'll do in a moment. First off, let's take a look at Excel. I'll show you how to do best fit line. Also, want to show you that for any kind of data, you can do a best fit line. Okay, you have to make sure you interpret it correctly and ask yourself if it's even reasonable for the data to be predicted by a straight line to begin with. So I said these are basically columns of random numbers between 0 and 10. What you want to do is just highlight those values, go to Insert, over to Charts, which is Scatter, and you just pick the first one. You have different options to pick the first one. Okay, so this is the scatter plot then of those values, and you see, you don't really see much of a pattern there. Maybe it looks like a slight, upward trend, but not much. Now, how do we do the regression lines? We're going to take any data value and right-click on it. See down here where it says Add Trend Line. Click on that. Now we give some options. Here it actually gives you several options for a trend line. So as I mentioned, there are several ways you can do regression lines. It doesn't just have to be linear. But we're going to use the linear case to make sure linear is checked. Also, what we want to do is definitely check where it says Display Equation on Chart. We want to do that. And that gives us actually, that's our regression line, the equation of that. Okay, you can also move it around. But let's go back here. Let's do one more thing. This isn't necessary, but let's also check what's called the R squared. So the small r, okay, if you remember, the small r is was your regression learned from the correlation, there's regression coefficient. This is just that value squared. So I actually take the square root of that, a square root of about 0.19. Do that quickly. About 0.19, the square root of that is about 0.44, okay, which is not necessarily a very strong correlation. Those appear maybe a slight upward trend as we saw, but as you expect, this is probably not a very good model for that data. Okay, as they say, it doesn't, although there's a slight upward trend, it doesn't really fit very well on a line. So what you'll see is even though you can certainly make a regression line for that data, it doesn't mean that's a good idea. It doesn't mean that's a good thing to use to actually then try to make predictions. If you try to predict a value, say right in here, where the data is, for example, we'll talk about the residuals. The predicted value for this data point is actually, that's the y value here, is way down here, which is not very good. Same thing for this data point. Predicted value for this data point here is actually right here, which is also not very good. Okay, now let's actually delete this because I don't need it anymore. Let's actually look at one more example. So I'm going to same thing, highlight this data. And also one more thing in Excel, whichever the leftmost column is, that's the one we'll treat as X. So remember that. So the same thing, go to Insert, charts, and then scatter. Okay, if you look at this data, it doesn't really look very linear, and it's not. Okay, this is actually from a parabola. But my point is, simply remember how to do this in Excel. You can essentially find a linear regression line for any data you want, but it doesn't mean it's a good idea to use it as a predictor. Okay, the same thing, right click on a data value, go to add trend line. Okay, make sure linear is clicked since we're talking about linear, and then click on display equation and chart. And this gives you the equation. See, actually, in this case, the best fit line is actually a straight line, horizontal line right there. Okay, so the point is simply that you can find this linear regression or best fit line for any data, but doesn't mean that's what you should use. It depends on if the data actually appears to have a linear trend. It looks like the data fits fairly well on a line or is actually predicted well by a line. This data is not predicted by a line. This data is very predicted by a parabola or a second order function. Okay, that's how you do then a regression line in Excel. We're going to focus most time on StatCrunch because StatCrunch will also combine what we need to do and also be able to use the correlation. So what we're going to do then, so I'm making predictions in the regression line, is say a few things. Let me just read this. Unlike a typical line in algebra class, this line does not go on forever. We can draw it forever, but at the same time, going on forever doesn't help. It only goes from the minimum value of x value provided in the sample to the maximum x value provided. Okay, so even though the line itself goes on forever, we're only going to consider basically focus on data values to predict data values between this value of x, this x right here, and this x. Okay, because going beyond that can be dangerous because although there might be a linear trend here in the data, and it might predict, well, this data, it could be something going on beyond far away that doesn't make a lot of sense to predict. Often we don't have that data, and there could be some other kind of trend going on, so you have to be careful about doing it. Trying to predict beyond the data you have is called extrapolation, and that can be dangerous if you do that. It says if the given x is not between the smallest and biggest x values of the sample, the line will not work effectively, should not be used to predict y. Doing so is called extrapolation. Extrapolation is predicting the value of unknown data points by projecting a function beyond the range of data points. That means, trying to pick something way over here or way over here. It may not be a good fit. We don't know much about the data over here, so it may not be a good predictor for that. It might give you a misleading result from what's actually happening. Now, this next 2 points are really important. If the graph of the regression line of the scatter plot confirms that the regression line fits the data well, okay, based on also your visual inspection, looking at it, it looks like the regression line, it looked like the data fits the line pretty well. And also the hypothesis test, the correlation like hypothesis test for a correlation we did in the previous video, use the regression line to predict values of y. If that's not the case, if the graph doesn't appear to be like a visual, if the data doesn't appear to fit on a line, or if we do a hypothesis test for correlation and we can't, there's not enough evidence to support the claim of correlation, we don't use the regression line. We actually use the mean of the y values instead. And we'll see an example like that here in a moment. Okay, and also here we talk about in the details how to create a regression line in both StatCrunch and also in Excel. So let's go ahead and look at our first example. So number one, what we want to do is we just want to create a regression line with this data and talk about how to do that. So let's go to StatCrunch. Now we have this data loaded in StatCrunch. Okay, in fact, that's this data right here. So what I want to do then, as it says on the other sheet, go to Stat, then to Regression. And this is the same path we went to find the correlation. Go to Simple Linear. Okay, it asks you to pick the X and Y, so make sure you pick the correct X and Y columns you want. I just use the X column right now for X and Y for Y for this example. And actually, that's really all we have to do. There are several options. That's all we're going to do. And actually, we're going to keep the same also hypothesis test for the slope. And let's get compute. Okay, now this is what you saw. If you saw my previous video in correlation, you saw this before. What we're going to do is we click on this box right here. And that gives us not only this not only gives us the scatter plot of this data, but also gives us the best fit line. It doesn't give the equation. The equation is actually on the other page. It actually does shows us the best fit line. Okay. Now, if you notice what's happening here, options, I believe I can copy this. Yeah, let's actually copy this and we'll take it back to our, I believe we can plot it and or print it over here. What we notice then, oops, let's actually go here. Okay. Sorry, maybe I can't do that. I was trying to copy it here. Well, let's actually go back. But what you can see is basically there's an outlier present. This data at least appears to be an outlier. Okay. It definitely doesn't fit the trend of the rest of the data. The value then definitely appears to be an outlier. So as we'll see, as you can see, the rest of the data, in fact, it does, lines up almost perfectly on a straight line. But because of this value here, it actually pulls the line in that direction. So you see the effect of even having like one outlier has in your data. So that's something to be careful for. Now, if you know a value is an outlier, you can remove it potentially. But if you're not sure, then you just have to be careful about that. That's the effect an outlier can have. Now let's actually go back here and get our equation of our line, regression line, which is actually this right here. In fact, let me just copy this. Don't copy all of it. Okay, and that's strange, but that's okay. So what we see here is our equation. Regression equation is y hat for estimate is given by this right here. So 3 point, I'll round it off to say 3 places, 002 plus 0.4997. That'd be 0.500x. Okay, so that's the best fit line for that data. Okay, then our R, correlation coefficient, our small r, is 0.816. That's found right here. Okay, so the regression equation and then the R. It also gives the R squared. We use the R. Okay, now, once again, as we saw, an outlier is present. And we can see how that affects our data. Okay, now something you can do on your own if you want to try this data on your own is actually then remove the outlier and see what happens, and you'll see this will actually fit almost exactly on a straight line. And your R, your equation will be different with different slope. Okay, you can tell the slope of the regression line is larger than the slope of this data right here, and then your your correlation coefficient R will actually be much closer to 1, positive 1. Okay, so that's the first one. All right, so now what we're going to do, let's take a look at our second example. We'll kind of explain in general how to do this method. So what we're going to do then, okay, it says, using the old faithful geyser data below, find the best predicted interval time after eruption, before an eruption duration of 253 seconds. How does it compare to the actual time after eruptions of 83 minutes, after eruption duration of 253 seconds? So what we're going to do then is we're going to find the regression line. Okay, we do a couple things. First, we want to do a hypothesis test for a linear correlation. This will tell us if it appears this data is, supports being a linear correlation to begin with. That'll tell us whether or not it's a good idea to actually use the regression line. So if you've seen, once again, from the previous video I did, your null hypothesis is that rho, the population correlation coefficient, is equal to 0, meaning there's no correlation. And then the H1 or the HA is it's not equal to 0. That means that there's enough evidence to say there is a correlation. Okay. Now, also, we didn't give an alpha value. Let's actually choose one to make alpha equals 0.05. That's our significance level. So what we're going to do then is actually, I already have this data plugged in. So we're going to do the same thing. And we can do this on StatCrunch. This will give us not only our information we need here, but then also our regression line and our scatter plot. Let's go back and take a look at that. I already have this data in. Okay, so that's this data right here. So once again, go to Stat, Regression, and Simple Linear. And once again, we're going to choose for X value, choose duration. And our Y value, choose interval after. Okay, now we're looking for the slope, our hypothesis test, and that's right here. And everything is set up correctly. You just hit compute. So what we want to do then is let's go and take a look at our data. Okay, now as you can see, this line here is our best fit line, the red line, and the blue dots then are our data. As you can see, it's not very linear. Okay, it may still be significant, but it doesn't seem very linear. So let's what we do then is, as we did before, let's actually stretch this out a bit. And actually, what I need is just this. So let's actually copy all of this into our Word document. And then we'll take what we need. Okay. So what we have then is actually our R 0.046 in 3 decimal places. Not very good. Okay. Our okay. Now here is actually our line. Okay, and it put it in terms of the names of the variables we gave in our table. So be aware of that. Okay. So basically, we're going to set Y equal to the interval, or Y hat equal interval after, and X equals the duration. And so then our line, our straight line, is going to be Y hat is equal to, I'm just going to say to 2 decimal places here. So 90 point, I'll go and do 3 to be consistent. 190 plus 0.007 X. Okay. That's our best fit line. Okay. That's that red line we saw in the graph. Okay. Let's take a look at a few more things we have. So actually our statistic here, our t-stat, we want the t-stat and the slope for both of these. So the t-stat is 0.104, and the p-value is equal to 0.9214. So once again, from the previous video in correlation, what we do then is we compare alpha to the p-value, and clearly the p-value is larger than alpha, which is 0.05. And so this means we do not reject HO. Okay, and actually go back and make a note so to make this more clear. So if we have this and we assume no linear correlation, and here if we take this, there is a linear correlation, just to abbreviate that. Okay, so what that means here, this is assuming no linear correlation exists. Here, this is basically saying there's enough evidence that the linear correlation does exist. So don't reject HO. So what that means then is there's not enough evidence of a linear correlation. Okay. So we will do a couple things here next. Is what that means is that we want to use the average or the mean Y to predict. Okay, so what that means is we're going to use the average value of Y to predict our other values. Okay, so what we're going to do is we actually do both. Okay, so and this is from the sample. So y average, and here we may actually have to go back. Let's go back to StatCrunch just a moment and see. I don't know if it actually gives us, it may not give us the, I guess it probably does not give us the average y and average here, and that's okay. We can actually find that without too much trouble. So what we're going to do is show you to do that. So if you want to do find an average of anything, go to stat, then summary stats, then for columns. Okay, so select the column you want. In this case, we want y. And basically, if you notice, they have all these chosen here, the yen, which is number, mean, variance, standard deviation, and so forth. Just click that. And what that's going to tell us then, oops, I apologize, I did the wrong one. So let's go back. So go to stat, summary stats, then columns. Actually, did the wrong value. I didn't want that. I wanted interval after. Sorry about that. Interval after. Do the same thing. And interval after gives all the values. The mean of the interval after is 91, let's say 91.714. Okay, right here. And that's from the data, 91.714. Now, if we compare, I'm kind of running out of room. Okay. So we're going to use line to use the best fit line to find the y hat for, or what it asks us to find that for. A duration of 253 seconds. What that means then, for x equals 253. Okay, so what we're going to do then, do our y hat, then is going to be, we're just going to plug that in, 90.190 plus point, I believe is 0.007 times x, which is 253. Let's plug that into our best fit line. Let's do that really quickly. 253 times 0.007 plus 90.19, and that turns out to be 91 rather, and try this on your own as well. 91 point, let's say 961. Now compare that, that's not too far off. The actual value, compare that to actual eruption of 83 minutes. Okay, so what we saw is actually, that's not a terribly good value. Of course, actually the mean is not the best predictor either. Okay, but neither one is really a great predictor for that. But at the same time, we're saying here that since we did the hypothesis test with a correlation and found that basically correlation tells us whether or not there's evidence of a linear correlation between the variables, since where there's not enough evidence to say there is a linear correlation. Based on what that's telling statistical sense, there's not enough evidence to use the best fit regression line as a predictor. Okay, so in that case, in a case like that, what you want to do then to predict the y values is the best thing to do is just use the average y value. It still may not be very good. In this case, it's not really any better, but it's still, it's kind of a better accepted to do that because there's not enough evidence to trust, statistical evidence to trust the best fit line. So that's the idea. Okay, of course, we can certainly use a predict. That's what we did right here to compare, but still, it's not a good idea if there's not enough evidence of a linear correlation. Okay, let's take a look at our next example. Maybe move it up here, and then we'll take a look. Okay, it says, the data below lists the old and new mile per gallon ratings for a sample of cars. Find the best predicted new mile per gallon rating for a car with an old mile per gallon rating of 30 miles per gallon. Is this likely to be a good predictor or not? So once again, let's do the same kind of thing. Let's also choose an alpha of 0.05. That's our significance level. Okay. We'll go through the same steps. We'll do a hypothesis test. or a linear correlation. Okay, so once again, H0 is going to be that the linear correlation of the population is 0. That means there's no linear correlation. We assume no linear correlation. Then H1 or HA is going to be that it's not equal to 0. There's basically that there's enough evidence to say there is a linear correlation. Okay, once again, follow the same steps we did here. Okay, so go to StatCrunch once again. I already have this data plugged in. So we'll do the exact same things. Okay, let's close that. Actually, I have that data over here to the right, old mile per gallon, new miles per gallon. Let's slide this over, you can see it. Okay, do the same thing, go to Stat, Regression, Simple Linear. Okay, so my X variable is going to be the old mile per gallon, old MPG. The Y variable is going to be new MPG or new miles per gallon. Once again, everything is basically set up to compute. And then as we did before, let's copy this information into our Word document, and so we can compare. Oh, also, let's take a look then also at our, so this is kind of actually where you want to start then, is actually take a look at your scatter plot. Here you see, this is a really, definitely very strong linear result. In fact, everything lines up almost exactly on a straight line. So this is definitely a case where you might looking and say, okay, this is definitely a case of linear relationship. So this is why I want to use a best fit line. You see the best fit line is a good predictor for almost every point. So now, as we expect, then this will probably be a significant result. It probably will be a strong linear correlation, and we'll see it is. So let's go back here. Let's plug this in. And once again, we'll pick out the information we need. Okay. And I'll go ahead and mention as we did before. So we're going to say let X equal the old mile per gallon rating, and Y hat is going to be the new miles per gallon rating. So we get our equation right here. And so this is going to be Y hat. The new is equal to, I'll do 3 places again, 0.808 plus 0.863x. So this is the old mile per gallon rating and the new rating. And our R right here is going to be go to 3 places, 0.998. So very strong as we expect. It's almost exactly on a straight line. Okay. Then from down here, we want to pick out our T-stat and our p-value. So the test statistic, the T-stat, is, you see it's really large, so 47.46. And then the p-value says it's less than, doesn't actually give us a value, it says it's less than 0.001, which is definitely less than alpha. Okay. Once again, compare the p-value with alpha. And so alpha is 0.05, 0.001. So clearly the p-value is left. So then we can reject HO. Okay. And this means there is enough evidence. I can spell enough. Of a linear correlation. I'll also abbreviate that. So linear. So basically this time, in our hypothesis test, there's enough evidence of a linear correlation. Okay. So we can use regression line for predictions. Remember, we said that because we had enough evidence, statistical evidence of a linear correlation. That means we can use the regression line it's reasonable to use a regression line for them to make predictions. Okay, remember the previous case that wasn't true. There's not enough evidence of a correlation, so we're going to use that case then to predict is actually the mean value of the y's, just the y's. Okay, in this case, we can use, there's enough evidence to say we can use the best fit regression line. Let's do that. So the question specifically asks us to find the best predicted miles per gallon for a car O rating of a 30 miles per gallon. Okay. I want to find y hat for x equals 30. So what I'm going to do then is take our equation line regression line we just found, okay, and plug that in. And so we have y hat is equal to 0.808 plus 0.863 times 30. And just do that on your calculator. So 30 times 0.863, then plus 0.808. Sorry, I actually made a quick mistake. So 30 times 0.863 plus 0.808. And that's going to be 26.698. About 26.698. Okay, so we look at our values closest to 30. Okay, so here's one for 33 for the old, about 29 for the new. Okay, or especially this one right here, 29 for the old, about 26 for the new. So that's actually pretty close. This is actually then turns out this is a pretty good predictor, and that's because, especially let's go back and take a look compared to the previous example of the old faithful data. If you look at our scatter plot, we see it lines up very well in a straight line. To make the old faithful data, if I can bring it back up. Maybe I can't easily. Basically, it was not a very good fit overall. So that's why not only was it not, there's not enough statistical evidence to say there's linear correlation. Also, as we saw, then the line itself wasn't a very good fit. And actually, the mean value wasn't a very good fit either. But that case is kind of the best we can do. And so in this case, then what we saw in both cases is what we're going to do then is do a hypothesis test, determine if there's a linear correlation. If there is linear, if there's enough evidence to reject the null hypothesis and say that there is evidence of a linear correlation, then use the best fit line as your predictor. If not, use the mean value of the y's of your sample data like we did in the first example. Okay. All right. So what we've learned today then is how to, what a regression line is, the basics where it comes from, how it's calculated. What we learned then is how to use it to make predictions. So what we said is, once repeating this once again, and I actually have this written down here, that if the regression line appears to be a good, if the data appears to fit very well on a straight line and the regression line seems to be a good fit, a good model of the data, and that's based up not only by looking at it, but also seeing if there is evidence of a linear correlation, then use that regression line to predict values of y. Okay. Now, also, but if not, if the line doesn't appear, if the data doesn't appear to fit very well on a line, or if there is not enough evidence to say there is a good linear correlation, then don't use that. Use the mean of the y data. Okay. Also, let's mention one more thing. Let's go back and take a look at our data in this last example. Now, talk about this idea of interpolation and extrapolation. Okay. Now, this line, I can plug in anything I want. I can plug in negative values of x, which would make sense to have negative miles per gallon. But I can also plug in, 300. So I get an estimate for 300 miles per gallon. Okay. But there's no car that gets 300 miles per gallon. So basically, the idea of what's called interpolation, basically you want to go between your highest and lowest, only between, or you want to predict only values between your highest and lowest x values. If you go beyond those values, that can be problematic because you don't know how well the data is still predicted by your model, because it may not be linear outside that range anymore. Okay, so then what we learned then is how to create a regression line and what it means and how to use it to predict. Thank you. Have a good day.